Hello, my name is Charles Wade. I am a PhD student in the Matter Assembly Computation Lab at the University of Colorado Boulder, and today I'm going to be talking to you about OpenVCAD, a volumetric multi-material design compiler. So, to get started, let's talk about where the state of multi-material 3D printing is. Well, on one hand, we have multi-material extrusion-based systems. So these include filament multiplexers or perhaps multi-build point systems. As they print, they switch between discrete material regions to print with different colors, different materials, or different material properties. On the other hand, we have inkjet systems. These offer much greater spatial freedom, allowing us to deposit small droplets that we treat as voxels anywhere within the print volume. This allows us to create complex material gradients and engineer the behavior of whatever part that we're building. So this talk is going to primarily be focused on inkjet systems, just because they offer the greatest spatial freedom and make the most sense to start with. However, these methods are applicable to other toolpath-based 3D printing systems. So what can we do with inkjet 3D printing? Well, one big application is functional materials. So combining materials with different properties together in a single part to engineer some kind of behavior. One of the big applications of that is soft robotics or compliant mechanisms. And then finally, we're also going to talk about this in pre-surgical planning models. So how does traditional multi-material design work? Well, it's centered around solid body modeling. This is primarily an artifact of historical 3D modeling, where we cared more about what the surface of an object looked like rather than the composition within it. So typically, if I want to print an object with two materials, I'll create two separate bodies that represent each discrete material region. I'll make them coincidental in slicing software, and then I'll slice that. On the other hand, inkjet systems typically use bitmap files. So these are image files that represent or each pixel represents a different material by assigning a different color. So in the bottom right-hand corner, you can see we can create these complex objects that have transparent regions that allow us to peer in the inside, or perhaps different mechanical behaviors at different regions of the part. So let's talk about some key limitations of these existing methods. Well, they can't really express volumetric composition, especially the solid body modeling. It's virtually impossible to create color or material gradients, and it doesn't really represent internal structures very well without having a bunch of different discrete material bodies. They tend to focus on the surface of the object. Like I said, this is a motivation from the original world of computer-aided design, where we were trying to make things that looked good in rendering. As we've moved into the world of 3D printing, we really need tools that actually express an object fully in 3D, including internally, right? So these tools generally lack efficient ways of visualizing internal compositions. And then finally, we really need for advanced applications, we require custom software. So this leads to a lot of situations where researchers right now are developing one-off scripts for designs. Perhaps I have a specific application, I want to make a specific part with a gradient, I'm going to write a MATLAB or a Python script to generate those specific files for my printer. There isn't a lot of good general purpose solutions. So really what this all comes down to is design software is actually limiting what our printers can construct. There's been tremendous advancements in the world of additive manufacturing machine capability, but there hasn't been corresponding advancements in the actual design software and methods for designing things for that. So our solution is called OpenVCAD. We call it a volumetric multi-material design compiler. So where existing methods define materials explicitly, so through those solid bodies or maybe as voxels or bitmaps, OpenVCAD instead defines things implicitly. So we use distributions and operations to build objects in a sort of compiled way to better express the complex material relationships within inside. So really, OpenVCAD acts like a blueprint for multi-material designs. So what does that look like? Well, this tree gives a good walkthrough of what we're conceptually doing. So very similar to something like OpenVCAD, the name similarity is intentional there, we use a compiled design. So we assemble things using constructive solid geometry with some extra nodes added on top of that. So in this case, we're able to use different leaf geometry nodes, so a sphere or a cone. We can translate, rotate, scale those around. We can perform Boolean operations to combine those into a single composite object. And then the real magic of OpenVCAD is within the multi-material nodes. These allow us to actually use mathematical expressions to describe how the materials should be comprised in the object. So, what does this architecture actually look like? Well, we use what we call the OpenVCAD modeling language. Given a printer configuration, these get combined with the OpenVCAD compiler, which generates or slices us a bitmap stack. And then finally, we can hand this bitmap stack to our 3D printer to construct. So all this bitmap stack really is a bunch of image files that represent a single layer. So this is a very common representation within inkjet printing. So what does this modeling language look like? Well, very similar to OpenVCAD, we use sort of a script and a script-based organization along with the tree structure. So kind of working from the inside out, here we can see we have geometry nodes. So in this case, a cube and a sphere. We're able to perform composition on those. So in this case, we take the difference. And then finally, we apply our material nodes. So here, we're creating a metamaterial composition where we have 20% red and 80% blue. You could think of these as potentially a stiff and a hard composition or composite materials that make a specific metamaterial that behaves in a desired way. So really, what we're doing under the hood is creating a tree that forms two functions. We can evaluate that tree for geometry, so that would be f of x, y, z, right? That's going to return our signed distance to the surface. This is a very common representation in computer rendering, but the other special function that we introduce here on top of this tree structure is a material evaluation. So given those same spatial coordinates, we should be able to return a material distribution or ID. So let's look at a practical example. This is a screwdriver that we designed in OpenVCAD and then printed on an inkjet system. And the script is shown above it. So it might look complicated, but I'll walk you through it. So kind of starting at the top here, we've gone ahead and defined our mesh as a screwdriver. So we've just imported some external geometry in, and we're going to perform a functional grade to give it these color and material regions. So this first token at the top says, okay, we want a distribution, or we want the material distribution to be 100% clear for any x coordinate less than or equal to 100 millimeters. So if we plot that on the graph, it's going to look something like this. Moving down, we can say, okay, now we want a crossfade. So when x is greater than 100 millimeters, we want to actually use a sigmoid function. So that's what you see there. The question mark in this expression is just a ternary operator that's saying if, right? If x is greater than 100, then run what's between the parentheses on the right, colon, or otherwise return 0. And then plot that, you can see we get that sigmoid function starting at 100. And then finally, if we want to look at what the color is for yellow, we can say while x is greater than 100 millimeters, we want to inverse that. We want the inverse of the sigmoid function to use to crossfade. And if we plot that, we can see something like this, right? So at any given point on this graph, I should be able to put my finger on it and say, okay, all of the compositions, all of the lines should sum to be 100%. And that represents the volume fraction at any given location in here. So let's step this up a little bit. In my title slide, I kind of showed this gradient that went across the OpenVCAD text. We could step it up a little bit more and make a multi-material gear. We can use other coordinate systems. So in this case, I'm using cylindrical coordinates. We're kind of grading as we move out across the radius of the cylinder. And perhaps, this has a mechanical motivation, a wear-resistant material in the teeth, but a cheaper and maybe lighter material in the inside of the gear. So what are the applications of this functional grading, right? The primary one is metamaterials, right? Meta here meaning beyond the capability of a single material. So these are going to be engineered structures that behave in specific ways. So in this case, you see on the bottom left, this is a graded gyroidal unit cell. So here we've created a gyroid geometric pattern, and then we've graded in a red material into the core. We could also create discrete material regions very easily with our functions. It doesn't have to be a gradient. In this case, this is another gyroidal unit cell, a cube in this case, where we've graded in a red material just in the inside with a hard transition to the blue on the outside. And then finally, this is really great for lattice structures. So OpenVCAD has the ability to go ahead and define lattice structures, both strut-based as well as other unit cell lattices, and tile those across space. But what's really awesome is we can use these multi-material nodes anywhere in our trees, right? So in the case of this lattice structure, we can define our individual struts. We can actually grade uniquely across each one of them, or uniformly across each one of them, and then composite them into one big structure. So one of the questions that might come up here is, well, how do I just blend adjacent materials together to create a smooth interface? Am I going to have to come up with a bunch of functions? What if I have a bunch of materials, right? So let's look at this example. I've got 4 simple materials defined next to each other. I just want to blend across them. Well, we could use functional grading, but we're going to need to make pretty complicated material distributions for that. Instead, we have a special node that we call convolution. So if you've ever done convolution with image processing before, this is going to seem fairly familiar. So what does that specifically look like? Well, let's just take the case of when we're sampling the tree into bitmap stacks, right? So let's say we have 2 materials, right? The lighter gray material A, the darker gray material B, and we want to sample the highlighted pixel location. We're going to define some kernel size around it, so in this case 3 by 3, and we're going to look at the distributions within those areas. So 67% one material, 33% the other. We're going to create a mask for those where the 1s represent material and 0s represent no material, and we're going to have one of these masks for every possible material in our design. We're going to multiply by our user-defined kernel. So these kernels can be virtually anything. If we've ever done image processing, this can be things like Gaussian blurring, feature detection, sharpening. There's a lot of existing kernels that can be used for image detection that apply perfectly here too. And we're going to multiply and sum up these user-defined kernels with our masks. That's going to modify the distribution within that window, right? So now we have 56 and 44. We can then feed that back into the weighted sampling process, and then when we actually go to assign that when sampling into bitmaps, we can replace that conditionally based on those probabilities. So let's talk about some of the applications of convolution. Well, one of the primary ones is medical image printing. So it's very common in the world of pre-surgical planning models to get MRI data that's fairly noisy. You know, we've brought it in, we've processed it, we've assigned materials, but those material assignments are never going to be perfect. Naturally, given the image processing, we're going to have some noise. So on the left-hand side, in A, you can see this is an original brain scan. There's a lot of matter and noise in those sort of cyan pixels kind of mixed in with the brain. We want to be able to clean that up, and a sharpening kernel offers us a really good way to do that. So when we actually do this, this is going to help us improve transparency, as well as it can be used to highlight specific regions. So that's what we see what's happening here on the right-hand side of the screen. We've got a fully printed brain model. So what does this medical image processing pipeline actually look like in VCAD? I kind of glossed over that first part, but the way it works is we take raw DICOM data for an MRI, we bring that in, and that's going to be an intensity field of the different matter. We say between specific ranges of that intensity field, we want this to be assigned to specific colors or materials. So perhaps the colors match, what the actual matter looks like, or make a good visual model, or the materials behave in specific ways that are similar to whatever tissue they might represent. We do that image processing to do the cleaning up, the highlighting, and then finally we use OpenVCAD to slice these things into a format that the printer can use. So one of the big problems here is that although MRI data is sampled at a regular uniform voxel resolution, it's very common for voxel-based 3D printers to have asymmetric voxel sizes that actually are derived from mechanical capabilities. So in this case, this is a key piece for actually slicing this into stacks and then giving yourself a printed model. So switching gears a little bit, let's talk about another really big application of OpenVCAD, and that's with designing soft actuators. So perhaps we have a soft actuator like this, where we want multiple materials. We're going to put pneumatic pressure in the inside. It's going to inflate these channels. You'll see kind of in the second image from the left there where the finger has inflated and bent. And depending on how we apply variable stiffness materials and gradients, it's going to change how the material or how the finger bends, at what rate and what degree. So multiple materials can be used to create this compliant mechanism, right? And the actuator also incorporates periodic geometry, right? We're repeating the same pattern over and over again. We could design this part, externally in traditional design tools like SolidWorks, but really with periodic geometry, it'd be good if we had a sort of functional representation for this, right? And then on top of that, we also want the material distributions to be periodic, right? So that same function that defines the geometry can be tweaked just a little bit to actually represent the material and the geometry. So actually putting that into practice, we provide what we call the FREP geometry node, or the functional representation. This is a scalar field, right? So defined here on the left, the different colors represent the distance to that surface, right? We can pass an ISO, or give this an ISO value and pass an ISO surface through this and actually get a sort of triangulated mesh that comes out of it using marching cubes. So say we give it this function, you don't need to focus specifically on the function, just know that it represents the gyroid infill pattern, and we can sample that in OpenVCAD to get this gyroid structure very easily. So how do we connect that in with the materials? Well, this is a very good example of using both geometry as well as material distributions functionally. So in this case, you can see in the bottom left with the tree definition, we start with a gyroid function. We also bring in an externally defined, or rather designed, wing structure. We perform an intersection, and then we functionally grade. So what's happening here is we're doing two things, is that we're decreasing the gyroid unit cell. So when we defined that gyroid function, we actually gave it spatial grading parameters that say, as we move out along the wingtip, we need to preserve our geometric detail, right? Because we can have rather sparse regions at the section of the wing on the left side that attaches to the plane, but at the very tip, we need to maintain that because we don't have a very large feature size, right? So we decrease the gyroid unit cell going out to maintain that. And then on top of that, we're actually cross-grading materials. So we've got the blue material that transitions to the red material. Perhaps this is, done for lightweighting or thermal characteristics. So one of the things that VCAD incorporates is real-time visualization. All the pictures you've seen thus far are generated like that. We provide two primary ways to visualize in this. One is using an ISO surface. So this is a surface-only visualization, right? It'll show us our material distributions. It's very fast, allows us to get a good idea of what something looks like very quickly, but it doesn't allow us to peer inside of it. On the other hand, we have sort of this GPU ray-traced version. So if you have an NVIDIA CUDA-capable GPU, you can actually visualize these things very quickly in parallel. In this case, this object's about 1 billion voxels. It takes a few seconds to generate, and you can visualize this in real time with shading. This just allows for sort of rapid design evaluation. And another thing we can do is control transparency, right? So this ray-traced version, we can actually peer better into the object. So let's talk about interoperability, right? OpenVCAD sounds great, but maybe sometimes you're going to need to export in a specific format for something else, or you want to bring geometry in that isn't, part of our tree structure. Well, I've already showed you meshes, right? So we can bring in triangulated meshes as STLs, 3MFs, a whole bunch of different formats. I've already talked about functions as well. Another thing we provide is constructive solid geometry primitives. So these things are spheres, cubes, rectangular prisms, cones, those sorts of objects. You can combine those through the transformations and the Boolean operations to create, composite objects. I talked a little bit about the DICOM. So DICOM is the medical scans. We can also bring in voxel grids, so specifically in the Open and Nano VDB grids. Right, so these are very popular libraries in the computer graphics and CGI world. So if you have externally defined grids, perhaps you did those in Blender or some other tool, you can bring those into OpenVCAD. And then finally, you can actually re-import bitmap stacks that you've already exported. So if you already have existing data or existing models that you've given to your 3D printer, and maybe you want to resample them or process them, you can bring them into VCAD and do some of the processing on them. And then for exporting, I've already talked about the bitmap stacks specifically for inkjet-based 3D printing systems. We also have volumetric finite elements. So this one allows us to export all of these, or sample the OpenVCAD tree into linear brick elements, and then take that into simulation software like Abacus. You can export as those open and nano VDB grids as well as BinVox. So if you want to try OpenVCAD, a compiled version of the program is available under a non-commercial license. This is sort of what is meant by OpenVCAD. That allows for academic and research use, hobbyist use. We just disallow any commercial use of OpenVCAD without obtaining a specific license. If you are a commercial entity, feel free to reach out to us and we can negotiate, as well as the source code. So the source code is also open source, but are under the same terms, but available by request. So if you want to get access, you can scan this QR code or go to matterassembly.org/OpenVCAD. That will take you to the website. That gives you a bunch of information. It will also lead you to our additive manufacturing publication, where you can read more about the specifics of what we're doing. You can also request access to the source code there. If you have any questions, you can contact me there at my email. And thanks for listening.